Okay, now we're going to talk about work, but we're going to get more specific into how to calculate work if you have a force. Oh, Claire, this is for you. How to calculate work if the force is at an angle to your displacement. And this is going to get pretty sophisticated. This is going to lead to a force versus position graph. And this will kind of lead us into a little bit of calculus. Then we're going to talk about power. What is power? How do you calculate it? And all this is, it's pretty cool. All right. Now, we said work. Work was the process of transferring energy from one system into another system by applying a force. For example, if you're riding a bicycle, you're applying forces, with your legs in cranking, the thing, and eventually a force is applied to, the system of you and the bicycle, and that force is actually the friction between the wheels and the ground, and that force pushes on you and does work and changes your energy. So you're transferring energy from the muscles in your legs to the motion of you rolling down the road. So that's what work is. Okay. Well, now we looked at this problem last time. If we had a crate, let me zoom in a little bit. So we had a crate, and we applied a force like this, and we said our displacement was like this, right? Well, let's actually do a problem. Let's say that this force here is 10 newtons. And this displacement is 3 meters. Okay, well, the work done is just the force times the displacement. So this would be 10 newtons times 3 meters. Well, 10 times 3 is 30. And a newton times a meter is a joule. So there's my answer. I did 30 joules of work going from here to here. Now that 30 joules of work is going to result in kinetic energy. Let's say this thing started from rest, and so it was moving when it got here. So all that energy that you put into it, all the work you did, transferred energy out of your body and put it into the kinetic energy, the motion of the crate. Okay? And however fast it's going, depends on its mass. But what if I did this? Suppose the crate was already moving, and someone was applying a force straight down. Now this thing's already moving, and it's going to move from here to here. Is this force right here, is it making it go faster and faster? Is this going to make the crate go faster as it moves along this horizontal plane? No. Only a force that has a component or is in the same direction as delta x, is that going to change the motion of that crate. So really this doesn't change anything. It's not transferring any energy into this crate. So there's something going on here, because over here, up here, the force did do work. It changed the motion of the crate. But this force is not changing the motion of the crate. It's not doing any work. Well, let's take a look at a situation like this. Let's combine these situations. What if I've got a force like this? Here's my force F. Now, there's no friction here, okay? Is this object going to change its velocity? Is it going to change its kinetic energy? Yeah, it's going to go faster and faster. But I think you can see that only part of the force is making that happen. Right? Only the component of the force it's in the same direction as the displacement. Here's my displacement vector. We call that delta x. Let me zoom in. Only this part of the force right here is changing the motion of this object. This component doesn't do anything. It doesn't change the motion of the crate at all. So it doesn't do any work. Now let's take this force and just kind of draw it down here. Here's my force. Here's my force vector. Here's my displacement. Do you see here? Here's the angle theta between them. Right? So this theta here, it would be this theta here. So if this is the part of the force that does work, what is that? Well, I think you would see this is F times what? It's the adjacent leg of this right triangle. It's a component of the force. It's in the same direction as the displacement. Cosine theta. So now we get to the simple regular physics definition of work. Work is equal to F cosine theta times delta x. Now, this means, hey, this is the part of the force that's in the same direction as delta x. Now, I'm restricting it here to delta x because that's what I drew in the problem. Let me rearrange it, though. This is F delta x cosine theta. Okay. Now, what if the object isn't moving in a delta x direction? What if it's moving in some arbitrary three-dimensional direction? I don't know. Well, instead of delta x, we'll just call it delta r. And we can say that work is equal to how big the force is, how big my displacement is, and I'm going to use delta r instead of delta x. Delta r can be in any direction, times the cosine theta, but theta is the angle between the force vector and the displacement vector. Now, you've done this before, most of you. I think you've done it in AM and in AMA, where you take two vectors and you multiply them together in such a way that you get a scalar, because work is a scalar. There's no direction associated with work. Anybody remember what that's called from AMA? When you multiply two vectors together and you get a scalar? Have you done vectors already? I think in AMA you have, right?
Yeah, I just
don't remember. That's okay. Okay. I know. Well, I'm just trying to relate what you're going to learn in math to what you're going to be doing in physics. I'll be honest with you, thinking of it in terms like this is pretty much good enough for this class. But let's go a little farther. This is called the dot product or the scalar product. Work is equal to F, I put a vector out on it with a big old fat dot, delta R. Now what does this big old fat dot right here, what does this mean? It's an operator. It's telling you to do something with the numbers that surround it, or with the quantities that surround it. It says, hey, I'm going to multiply these two vectors in such a way that I get a scalar. And here's what we want you to do. Take how big, or the magnitude of the force, multiply it by the magnitude of the second vector here, delta R, and then multiply that by the cosine of the angle that you get when you draw these so that they're tail to tail. Well, this is called the scalar product. And they call it the scalar product because you're multiplying two vectors and you get a scalar. But sometimes it's called the dot product. product. Because the operator we use is a great big dot. Okay? So you will use this a little bit. Okay, and we'll do some example problems here in a little while. So this is our definition for work, and this is about as sophisticated as we get. Now, let's talk about one more thing. Oh, well, two more things. Let's talk about a force versus time graph. Let's suppose I look back at my example problem right. Nah, let's not use that one. Let's do an example problem. Example. Given you have a force that's equal to 3 newtons. You have a delta x that's equal to 5 meters. Fine. Now let's say the force is in the x direction. We don't have to worry about the cosine theta or anything. Find the work done. Okay, this is pretty hard. Work equals force times displacement. So what is that equal to? Can you do this? Can you do the math in your head? Oh, it's 3 newtons times 5 meters. Okay, what is it? 3 times 5. 15. What's a newton times a meter? There's my answer. Okay. Wow, that was pretty tough. Now, but here's something that we've done over and over again this year. We're going to do it again. Whenever one quantity is the product of 2 other quantities, you can draw a graph. Now, why would you on this problem? Well, you wouldn't. But there are some problems you would. But I want to show you with this one. Force, position. Well, let's just say that our initial position was 0. And we're going to go 5 meters. 1, 2, 3, 4, 5. And this is position in meters. And what's our force? 3 newtons. So we'll go 1, 2, 3 newtons. 1, 2, 3. This is force in newtons. Now, what's true about the force as we move? The force was constant. It was 3 newtons the whole time, or the whole way, all the way across here. Okay? And so I think you can see that when you multiply the width is 5 meters and the height is 3 newtons. So the area underneath this graph represents work. Look, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 squares. Each square represents 1 joule of work done by this force. Do you recognize this? I mean, we've done this with, when we multiplied velocity as a function of time, the area underneath that graph was a change in position. When I graphed acceleration as a function of time, the area underneath that graph was a change in velocity. When we graphed force as a function of time, the area underneath that graph was impulse or change in momentum. Now we're graphing force as a function of position. The area underneath that graph is work. The transfer of energy. Now, of course, you wouldn't do that for this problem. The force is constant. It's just a rectangle, big deal. But I could give you a problem like this, and you can run into problems like this where the force is not a constant. So let's do this, okay? 1, 2, 3, 4, 5. This is position in meters. 10, 20, 30, 40. I'm just making this up. This is force in newtons. What if you had like a spring or something, a strange mechanism that was applying forces to things, and it was doing something like this? Let's have it go to the 2 and then to the 4, and then we'll have it come down steeply like this. Well, you can't just go force times displacement. You can't just say 40 newtons times 5 meters, because that would be too much work. So how would I figure out how much work is done here? I figure out how much work was done here, and how much work was done here, and then how much work was done here, and I would just add them together. The area underneath a force versus position graph represents work. Well, how much is here? Well, what's 2 times 40 is 80. 80 divided by 2 because it's a triangle? 40 joules. And what do we got here? 2 times 40. This is 80 joules. And what have we got here? 40 times 1 meter is 40 joules, but then we divide by 2. 20 joules. So how much work was done by this force that varied? Well, 120, 140 joules. Is that right? Okay. Now, in calculus and in calculus-based physics, we can go farther than that. We would just take this and divide it up into infinitely skinny little rectangles, and we would sum them up. Here we're summing, right? 40 plus 80 plus 20. Well, in calculus, we would say, oh, this is the integral of force as a function of x times, and each width of this is a little tiny delta x. Instead of calling it delta x, we would call it dx. And you would have some initial position and some final position. This is for those of you who might be in calculus right now. Don't worry, you'll not do this in regular physics on a test in here or on any of the homework, but I'm showing it to you. Hey, this is what you're doing in calculus. Well, even this isn't advanced. I'm now going to give you the ultimate equation for calculating work. You do this in AP Physics, which I hope a lot of you take next year. It's force dotted with a little tiny, this is force times a little tiny displacement, and you go from some initial position to some final position. Thank you. Saber, this is for you. All right, now don't worry about this. Some of you are going to be taking those of you in AMA, you're going to be getting the integral calculus very soon. And you'll all have done dot products. So, you're going to see this sort of thing. And this is the application for it. Okay. Last thing we're going to talk about today before we start working example problems. Let's talk about power. Okay? Power is defined to be the rate at which energy is transferred. Power is the rate at which energy is transferred from one system into another system. Okay? How fast are you moving the energy? Now, of course, right now the only transfer of energy we've really been talking about is work. The same, though, is true for heating and radiating and all the other forms of energy transfer we're going to talk about later. But right now, let's just stick with work. So the power is equal to the work that has been done. And this is the general definition, divided by the time it took to do that work. Okay, so this is work, right? Well, let's take a look at in terms of units. What are the units for work? Joules. What are the units for time? Seconds. A joule per second. So if you're doing, like if you're lifting something up fairly light, my cup of coffee here, if I pick this thing up, if I take the amount of work I did and divide it by the time it took me to do that work, that would be how much power I'm putting out. Well, a joule per second has a name. Anybody know what that name is? Anybody know what that name is? It's a watt, yeah. It's a watt. A joule per second is called a watt, and it's abbreviated with a capital W. Now you got to be careful here, because what else do we use capital W for? Work. But that's when it's a variable. When capital W is a unit, it means watts. Okay, so if you take the work done and divide it by the time, you will get the power of something. Okay, so power is equal to work over time. Oh, I already wrote that, so that's good enough. So in some of the problems we'll do, it'll ask you how much power is something putting out. Just take how much energy was transferred, divide it by the time it took to do that, and that's the average power that was done. And that's good enough for now. We'll do a little bit more with power later on. But that is all for now.